Okay, thanks a lot. So I'll talk about a gradient boosting algorithm which doesn't have hyperparameters. So you can use it without hyperparameter optimization. Half of the talk will be about gradient boosting machines, and the other half will be about Rust. Gradient boosting machine is an algorithm where you iteratively train decision trees based on residuals. At each boosting round, you basically learn the residuals before after the previous rounds. So it iteratively learn the residuals, the errors of the previous rounds. So at the end, you get a bunch of decision trees, and you make predictions with the sum of all decision trees. Actually, this residual calculation comes from mean squared error, the derivative of mean squared error. So this is a special case of regression. And gradient boosting machines are very popular. They perform better than neural networks for tabular data because they are robust to uninformative features or noise features, and they are capable to preserve the orientation of the data, and they are able to easily learn irregular functions. So you can check this first reference, first paper, and another paper is about they check XGBoost, and they saw that XGBoost outperforms deep learning models on tabular data, and it is because it's hard to optimize deep neural networks compared to XGBoost. So you can check these papers, and you can see that gradient boosting machines outperform neural networks for tabular data. Gradient boosting machines have a lot of hyperparameters like max depth, max leaves, L1 regularization, L2 regularization, etc. So you need to carry out hyperparameter optimization for the best performance. In this new kind of gradient boosting machine, we removed all of the hyperparameters. So you don't have any hyperparameter. You don't have carry out hyperparameter optimization. We did this with a generalization calculation, and the remaining parameters do not need to be tuned. So you know these parameters before fitting the algorithm, like base score, ambience, and you don't set actually most of them. You can just use default values. My initial this Perpetaul booster is a fork of this genome forest library. So this is the initial version, and I forked this library and created this API. So this is the generalization calculation. Basically, we calculate the loss before the split, and we again calculate loss after the split, and we create a separate validation data. We check if loss decreases with the validation data. If loss increases in validation data, we reject that split, and we don't further split that node. And if validation loss decreases after the split, we continue splitting. So this is a simplified version of generalization calculation. Thanks to this generalization logic, we were able to remove all of the hyperparameters. And these are the benchmark results. Usually, hyperparameter optimization takes 100 iterations. Since we achieve the same result in a single run, we are able to achieve around 100 times speed up compared to light GBM for different budget levels and different estimators. And we are able to achieve this by using Rust. For example, we are calculating cumulative gradients and cumulative Hessians during split finding. For example, we are using arrays instead of vectors, using while calculating these cumulative gradients and Hessians, because using vectors instead of arrays here cause a lot of allocation overhead. So we saw that using arrays for small lists provides a lot of improvements in terms of performance due to faster access and faster allocation. And we are using vectors, especially for histograms, for large and growable lists, because histograms or number of bins in histograms depend on the number of features. And we are initializing these histograms as soon as we know the size of the vector, and we are using mutable references because we don't want to allocate every time we need them. So we are initializing them at the beginning of the algorithm of fitting process, and we are mutating them during fitting. And another problem that we during mutation we had to use mutable references from a vector, but it is not possible to get multiple mutable references from a vector or hash map because Rust does not allow this. You can split a vector into and get two mutable references, but you cannot get multiple references or multiple mutable elements from a vector. So we had to use hash-brown hashmap for this. We were able to get mutable references to separate elements from a hashmap with hash-brown. And this hash-brown library is also a part of Rust-lang. And this feature gets many mutable elements. Feature is also available on nightly builds of standard library hashmap. But until this is stabilized, we decided to use hash-brown hashmap to get multiple mutable elements. So another trick was that we are using a data container to store our user input, user data frame. We are storing user data frame in a contiguous column major matrix for better cache locality, because otherwise we will have a lot of cache hits. So we have to use contiguous column major matrix to get the best performance. So that was about my talk. If you have any question, I can answer.
Mutlu, my question is at the very end. Are you aware of the fair crate? Because the matrix structure you defined is equivalent to the matrices that are in fair, and they're already pretty tightly optimized for these kinds of problems.
Do you mean another library? I don't get that part. Fair. This is an external library, right?
Yes.
Okay. I didn't see this library, but yes, I should definitely check. But this is just a container, data container, because we don't want to copy the user input. So here we have a reference to the user data, because users are already have their data in memory. So this is just a container. If that library has that kind of feature, I will definitely.
Yeah, that would be the matref structure, which is generic over strides and so on.
Yeah, that's great. I will definitely check.
Great. There's at the moment no other question yet in the chat. Another question for myself. I mean, you rightly said that for small data structures, you're using stack-based direct arrays for fixed sizes. Have you thought about, or is this even relevant for you, that, for example, you could adapt the sizes with pop macros or generic parameters? Are you thinking about this?
Currently, we don't have to make this generic, this five count, this
Yeah,
five, number five comes from
yeah,
cross-validation, number
yeah.
of faults in cross-validation. Uh, Currently, we didn't have to make it generic, but yeah, in the future, we can consider it to make it generic. And yeah, if we see some benefits, we didn't experiment it with different number of faults yet. So if we see some benefit with different number of faults, of there is some user request about them, we should make it generic so that users can set it